Hey guys, so today we'll talk about sum to product and product to sum formulas. Every time you see sum to product, that means a sum of trig functions to a product, and a product of trig functions to a sum. So what I mean is, if you have sine of x plus cosine of y, that can be represented, or plus sine of y. This is just an example. Can be represented as sine something, cosine something, or something else. So what we have here are the formulas for product to sum. These are the product to sum formulas. If you want to change a product of two trig functions into a sum or a difference, because the difference is addition of a negative, if you want to change them into a sum, then these are the formulas you use. And I'm just going to show you where at least one of these comes from. I'm going to show you where this comes from, just so you don't think these are out of the blue. They come from the addition formulas for sine and cosine that we already know. You guys remember, if you check your note card, that sine of alpha plus beta is, if expanded, sine alpha cosine beta plus cosine alpha sine beta. And you also remember that sine of alpha minus beta, if expanded, gives you sine alpha cosine beta minus cosine alpha sine beta. Now, because mathematicians are experimentalists, some guy, whoever did this first, wondered what would happen if I added these two equations. If I added these two expressions, what would happen? So that's why you see this plus over there, that plus. So if you add these two equations, on the left hand side I have sine alpha plus beta plus sine alpha minus beta, and I hope you see that that's where this portion comes from. Sine alpha plus beta plus sine alpha minus beta. That's where that's coming from. And then on the right hand side, I'll have this term, this term that I've highlighted in green, and this term right below it are the same exact thing. They're both sine alpha cosine beta. So since they are the same exact thing, I can say I have two of the same exact thing. So 2 sine alpha cosine beta. And this term over here, cosine alpha sine beta and cosine alpha sine beta in the bottom, are the same exact thing, but they have different signs. So if I'm adding two things that have different signs and they're exactly the same, they cancel out. So if I want to express the sum, if I want to make this the subject, sine alpha cosine beta, because it's the product, then I'm going to divide both sides by 2. I'm going to divide both sides by 2. So I'll end up with sine alpha cosine beta on the right hand side is equal to sine alpha plus beta plus sine alpha minus beta. Everything is divided by 2, so it's the same thing as multiplying it by half. And if you just rewrite it and put this on this side and the other thing on the other side, this is what I'm saying. If I rewrite it as sine alpha cosine beta is equal to 1/2 sine of alpha plus beta plus sine of alpha minus beta. Then I have the formula for transforming something that was a product of two functions into a sum, right? Into a sum of sines, or into a sum of cosines, or whichever the question required. So I know this might look like a lot, but think of it as, if it's a product and you're taking it to a sum, then it's equal to 1/2 sine sum of the angles plus sine difference of the angles, because this is the sum of the angles and this is the difference of the angles. So you can prove all of the other formulas, you can prove all of these ones, and of course no one will ever ask you to prove them, at least at this level. Maybe at college, but not at this level. but you can prove all of these formulas using this idea of getting them from the expansion or the addition formulas for sine and cosine. So let's try to use them. I want to rewrite the product that's given here as a sum or difference. I'm going to look at the product. Don't let the big numbers and the x's and anything shake you down or scare you. Look at the functions that are forming the product. It's cosine and cosine. Go to your note card and ask yourself which of these formulas can I use for this expression. So cosine and cosine, a product of two cosines is over here, and that's expressed as half, open brackets, cosine difference of the angles plus cosine sum of the angles. So that's what I'm going to go do. I'm going to ignore the 20, put it on the outside. I mean, not ignore, but I'll deal with it later. So on the inside, I have cosine 36x times cosine 6x. Now, this product of two cosines is going to turn into open brackets half, open another bracket, cosine difference of the angles. So cosine, the difference of the angles is 36 minus 6, which is 30 degrees, and plus cosine sum of the angles. Cosine sum of the angles, 36 plus 6 is 42. I forgot an x here. Is 42x. So now I can consider the 20 and the half. When the 20 multiplies the half, I have 10, open brackets, cosine 30x plus cosine 42x. I have expressed an expression that was initially a product as a sum of two cosines, as a sum of two functions. So that's it. The only thing you need to make sure of is you're doing the addition correctly. So I hope you can check my math and see if I added that correctly. Now we've looked at product to sum. You can also do sum to product. Now this one might look a bit intimidating at first, but it's basically the same thing as this formula here in reverse, right? If you look at this formula, and I wish let me try to copy paste it so I can show you it's the same thing. Obviously, you don't need. No one will ever ask you to prove them, so I'm just doing them because if there are any curious people wondering why these things are the way they are, maybe this can help you appreciate that before you move on. So these are the product to sum formulas, and these are the sum to product formulas. What am I doing? These were product to sum, yes, and these are sum to product. Oh, these are not the right formulas. These are basically the same as the last ones. It's the wrong thing. Oh yeah, sorry, I was hiding. These are the correct. These ones that you see, sum to product, because it's starting from a sum going to a product. Sorry about that. So just want to put it on the side here, just so I can help you see that they are the same things, right? So these are sum to product, and these are product to sum. So I want to focus on this one, sine alpha cosine beta, because it's the easy one that comes from addition of two sine addition formulas, and then this one, because it's basically the same thing as that one. So in this formula over here, if I try to put in an interesting substitution, let me say that x, just because, like I said, mathematicians are experimentalists. If x is alpha plus beta divided by 2, right? And if y is alpha minus beta divided by 2, then what happens when I have x plus y? X plus y is going to be, if you add these two fractions, you add these two fractions, it's going to be alpha plus beta over 2 plus alpha minus beta over 2, which if you simplify, you will get 2 alpha minus 2 beta over 2, which is basically just alpha. So x plus y is equal to alpha, right? And if I subtract x minus y, it will be alpha plus beta over 2 minus alpha minus beta over 2. And when I work that out, what I will get finally will just be beta. So this shows me something, that when I have x plus y is alpha, x minus y is beta. So if I come to this expression, because I know that sine of x plus y plus sine of x minus y, right? If I do the operation, you guys remember I did this expansion in the very first step, and I got 2 sine x cosine y, right? You remember from the very first slide. Oops. Yeah, over here I did that addition, this portion of that section where I got 2 sine alpha cosine beta. So when I do that addition and I get this expression, then I'm just going to go ahead and substitute for these new conditions that I set. That's the word there. I'm going to substitute for these new conditions. Instead of x plus y, I know that when I add x plus y, I get alpha. So I'll just put this as alpha, right? And instead of x minus y, I know that when I subtract x minus y, I get beta. And then on this side, x alone, remember I set x alone to be alpha plus beta over 2. So this is sine alpha plus beta over 2. And y alone is alpha minus beta over 2. So it's simply coming from the same initial functions, same expressions. I know they look long and they look threatening, but don't be confused by them. One simple way of thinking about this is, if I'm adding 2 sines, I can turn them into a product by taking one, for example, 2 sine the sum of the angles divided by 2, and cosine the difference of the angles divided by 2. So in each case you have a sum and a difference. I have a sum here and a difference, and just like here I had a sum and a difference. So that's the common theme in sum to product and product to sum. Anyways, too much about that. Let me just go ahead and work through how to apply or use those formulas. So the problem we have here is the question is asking us to write the sum or difference as a product. Now one thing that I advise you to do is to first rewrite, if this is not a negative, first rewrite them such that the big angle is coming first, because that way you don't have to deal with the negative when you're working out the difference part. So if I write this with the big angle coming first, it will be sine 7x plus sine of 3x. Now I'm just going to go and look at my sum to product formulas and see where I have a sum of 2 sines. It's the very first one. I have a sum of 2 sines. When I'm adding 2 sines, it becomes 2 times sine, sum of the angles, cosine, difference of the angles. So this is going to become 2 sine. The sum of the angles is 7x plus 3x divided by 2. And the difference of the angles, this is cosine, difference of the angles, 7x minus 3x divided by 2. You don't even have to write this out. I'm just writing it out because yeah, you don't have to write it out. You can just go direct from here to say this is sine 10 over 2 is 5x, cosine 7 minus 2 is 4 over 2, 2x. Boom. You've turned the sum into a product. Let's look at another example. This is another product that I need to turn into a sum. And again, if this angle, if for example this 15 was the bigger angle, if it was the bigger angle, then my advice is first you write it such that the big angle is coming first, then you go to the formulas and look for which one has that expression, because it's going to be one of the expressions as long as you get the order right the first time. So this is the product of sine and cosine. This is product to sum. I need to express it as a sum, and I need to evaluate to find the answer. So which of these formulas is the product of sine and cosine? It's the third one here. What does it turn to? Half sine sum of the angles plus sine difference of the angles. This is going to turn into half sine, open brackets, yeah, very big brackets. The big brackets are supposed to be here. Sum of the angles 195 plus 15 is 210 plus sine difference of the angles 195 minus 15 is 180. Is that sine or cosine? It's sine. 180. Sine, yeah. So I have sine 110. I know that sine 110 is going to be negative because it's in the third quadrant, and in that third quadrant, tan is the only positive one. So I expect this to be negative, and the acute angle is 30 degrees plus half. Sine 180 is also, no, that's going to be positive, but 180 has the same acute angle as 0 degrees. I know that the sine of 30 is a half, but it's negative. The sine of 0 is 0, so my final answer is just negative 1 out of 4. I have worked this out without using a calculator and by using the sum, product sum formulas. And as you work through these, I hope you appreciate the application or the ease that this brought to mathematicians of long ago that did not have access to calculators, and how genius those guys were. Just cool stuff. Alright, we write the sum or difference as a product of two functions. Live in terms of sine and cosine. This is a difference of cosines, right? So I need to be using the sum to product formulas. I just go to my formulas and look for which one is a difference of cosines. It's the last one. What is it going to become? Negative 2 sine, sum of the angles, sine, difference of the angles. Divided by 2, divided by 2. So I'll just substitute. This is going to be equal to negative 2 sine, sum of the angles, 58 plus 12 is 70 degrees over 2 times sine, difference of the angles, 58 minus 12 is 46 divided by 2 is 46. Yeah. Alright. So if I just simplify this, this is going to be negative 2 sine 35 sine 23. Finished. You will find that these things are easier than you fear as you work them through, more and more and get the practice. Lastly, if I need to prove this identity again, when you look at this, please don't panic. Yeah, don't panic, don't get scared. This is what I need to express in terms of this, right? Now, I'm going to absolutely ignore what's on the right hand side because I know they want me to use this to prove that it's equal to that. Whatever it looks like, I'm going to first ignore it, and then I'm going to first simplify what's on the left hand side. After I have simplified it, I can look for patterns here that can look like what they want me to prove. So, first of all, in the numerator of this expression, I have a product. I have a product that I need to turn into a sum, because that's the first thing I see. So I'm going to use the product to sum formula, and it's a product of cosine and sine. Cosine and sine is over here, and it's going to break down into half sine sum of the angles, sine difference of the angles. So I'll put the 6 on the outside because that will deal with the half later. Then the half goes on the inside times sine, because it's cosine sine is equal to that. So sine sum of the angles, which is 8 plus 2, that's 10x, minus sine, difference of the angles, 8 minus 2 is 6x. Okay, that is the numerator alone. In the denominator, I have sine negative 6x. I know this is an odd function, so I can write it the same way as negative sine 6x. Now from here, I can simplify. In the numerator, I have 6 and a 2.5 that can multiply. When the 6 goes inside, that becomes 3 sine 10x minus 3 sine 6x. And in the denominator, I have just negative sine 6x. Now, at this stage, I can look at what they need me to prove, right? I can see a 3 sine 10, I already have sine 10 in my expression. I can see a cosecant 6x, so something is dividing by sine 6x, which I can create from my expression. And I have a positive 3. So because of this positive 3, this expression is asking me to separate the fraction. Separating the fraction, I hope you remember, a plus b over c is the same thing as a over c plus b over c. So I'm going to separate the fraction that way. I'm going to have, instead of 3 sine 10x minus 3 sine 6x, I'm going to separate the fraction into 3 sine 10x divided by negative sine 6x minus 3 sine 6x divided by negative sine 6x. Now technically, this negative is with this 3. So I can turn this into a positive and keep that a negative. It's still the same thing. I'm just doing that so I can cancel out the negative respectfully without causing any outrage. Okay, so 3 sine 10x divided by negative sine 6x is just negative 3 sine 10x. I'm doing this very slowly, times 1 out of sine 6x plus the two negatives cancel out. This negative and that negative cancel out to give me a positive. Sine 6x in the numerator crosses out with sine 6x in the denominator. So then I end up with just positive 3. So I have negative 3 sine 10x times 1 over sine 6x is the same thing as cosecant 6x plus 3. I have proved what they asked me to prove, and yeah. So this is your homework. I know there might be some questions, so we'll go over them in class tomorrow. Bye.